Hi, welcome to our new online format. So what I'm going to do is I'm going to do test 2 review today. So it's stuff we've gone over in class before, but with our extra break, maybe we've forgotten a bit and maybe it's time to relook at it. We're going to have the test on Monday, put an M back in, Monday, March 3rd. Yes. So that's when we're going to be looking at doing test 2, and it will be online. And let's talk a bit more about that. Okay, so like I said, online, it's going to be multiple choice. It's going to be like your online quiz. It's just longer. I'll make it available from the start of the class, which is 3 p.m., and I'll leave it available until midnight. You're going to have 3 hours to do it, but only one attempt. And I'm going to have it sitting here in the test 2 module, which is where you hopefully found these slides as well. So our topics for this test, same things we said before. The distance, velocity, time concepts, and the velocity, acceleration, time from our chapter 15 in motion. And I think chapter 14 is the circuit stuff. So now we're going to do some review. All right, so let's look at the distance, velocity, time graphs. And in this case, I've given you a graph. I haven't filled in the table, so let's assume these are kilometers. And we're just going to look at the graph and fill in the table. So at noon, we can see that we're at 120 kilometers. Okay, at 12:30, and these are going to be approximate. The spacing between the two, the y-axis is 20 kilometers, so maybe that's 141. And keep going at 1 o'clock, maybe that's 167. At 1:30, could be 194. At 2 o'clock, could be 235. At 2:30, could be 240. And then at 3 o'clock, maybe 256. Kind of maxing out at 280. And then the graph goes down at 4 o'clock. We're at 255 kilometers. Okay. So let's revisit slope. Slope, as we said before, is a rise, which is a change in the y, over the run, which is a change in the x. So in this case, if we're looking at a distance time graph, the rise is the change in the distance. And I'm just going to pick 2 really nice points to use here. And I'm going to do, I'm not really good at drawing straight lines yet, nor maybe will I ever be. I'm going to look at, woo, God, I'm trying to be on the 120, and that didn't work. And I'm going to look at this triangle here. That is terrible. So if I'm doing this, I'm kind of looking at an average slope between noon and 3:30. So between noon and 3:30, that's 3.5 hours. So I'm going to put it as 3.5 hours. That's my change in x, my change in time. And if you look here, I'm at 280 at the top, and I started at 120. So the change in distance is 280 minus 120 equals 160 kilometers. Okay, so if I take that back up to my formula, the rise of that particular triangle is 160, and the run is 3.5. And that will give us our slope, which apparently I didn't do the math for. So what will that represent? That will represent the average velocity between noon and 3:30. Now, of course, there's times where the velocity doesn't look like that kind of line. Like here, it does, oh my God, it does look like that, but, you know, if only I could draw this triangle. But at other times, you know, it looks a little different, and that's fine. You can have that, but when you get an average velocity between 2 things, you're just always going to pick those points, and you will be making a straight line, a slope between the 2 of them. Okay, so let's say we wanted to know what the average velocity between 12 and 12:30 was. So you can either look at your graph. I'm going to look at my table. I'm going to see at 12:30, and I know velocity is distance over time, or rise over run, and that's all I'm going to use with this thing. At 12:30, I was going 141. At 12, I was going 120. So I want the difference between 141 minus 120. And the difference between 12:30 and 12 o'clock is half an hour, 0.5. So my average velocity between 12 and 12:30 is this math, which should give me 42 kilometers an hour. Very good. Okay, now what about something like between 3 and 4 p.m.? So if I look over, hold on, let me see if I can switch this. 1 second, there we go. If I look over my graph here between 3 and 4, something different happened. So, I mean, if you wanted to look just at the table and do this without really paying attention to the graph and what's going on, you might do a calculation like, and I'm going to put it over here, you know, at 4 o'clock I was going 255. And at 3 o'clock, or I was at distance marker, pardon me, I was at distance marker 256. And you know, that's 1 hour. So I have -1 over 1 equals, my velocity was -1. And that doesn't make sense. So in a case like that where the velocity is changing, you kind of have to do a little bit of extra math. So that's not what you're going to do. You're going to be like, okay, what distance did I cover between 3 and 3:30? Well, that's 280 minus 255. I'm going to put some brackets around that. And I'm going to have to add in the distance I covered, even though it was in a different direction, between, minus 256. The distance that I covered between 3:30 and 4. And I'm going to make that positive. I'm going to do 280 minus 255. And that's what I'll divide by 1. So in this case, you're going to get 25 plus 24 divided by 1. And your math should work out to 49. Oh, good Lord. What? Hold on. Going back. Bear with me. Okay. 49 kilometers per hour. So a little different than what you expected, maybe. And when you're on these graphs, we have to think about what a positive slope means. A positive slope, you know, your velocity is positive, you are driving away from a point. But if you see a negative slope, that doesn't mean you have negative speed. And I don't really have a concept of what that means. It means you've kind of turned around and you're driving back towards the start. So whenever you see the graph going down, and I'm afraid to go over there because of the craziness of these slides, that means the slope is negative. Looking at a graph and trying to find maximum or minimum velocity. If we're looking for maximum, I'm thinking here, when you covered the most distance in the same amount of time. Okay, so that when you have that maximum distance, that's when you have that maximum velocity. When do you have the minimum? Not when it's negative, but when it's closest to flat, right? That means you didn't go very far, so your velocity was slow. What could have happened here? Maybe you stopped. Maybe you were in a traffic jam, stuff like that. So let's look at some calculations. Okay, here's where we want to be. Distance, velocity, time calculations. These are our formulas. It's the same formula rearranged, right? So here's slope equals rise over run, and here's all the variations that you get from that. So number 1, we're driving at a certain speed, and a song comes on, and the song is long. And I actually got this from the textbook, which made me laugh. It ends 7 minutes and 55 seconds later. How far did you drive during the song? So let's look at our units, 83 kilometers an hour. So I want to take that time, that 7 minutes and 55 seconds, and I want to make sure that I am changing it into hours. So we start by taking the seconds, and we're going to change them into minutes with this math. And 55 divided by 60 should give you 0.92 minutes. So I have 0.92 minutes, but I already had 7 minutes. So now I know that my time, 7 minutes 55 seconds, is the same as 7.92 minutes. And guess what? I'm going to have to divide that by 60 again, because that will make hours. And when I do that math, I get 0.13 hours. Excellent. Okay, so what am I solving for? I'm looking for distance. And according to my formulas, distance is equal to velocity multiplied by time. So I've got my 83 kilometers an hour. I've got my 0.13 hours. And we're going to do that math, and we're going to end up with 10.95 kilometers. You almost drove 11 kilometers during the time that song was on. And now let's look at number 2, a little more comprehension here. Okay, so we've got some time, we've got some distance, we're solving for velocity. So let's try and understand what's happening. It looks like we drove to a dealership, and that took us a certain amount of time. And then we were hanging out at the dealership for a while, and then we drove back. So for time, we have two time segments that are important. We have, oh no, Nelly, what was that? Okay, there we go. We have 10:47 minus 10:15. So leaving our warehouse and driving to the dealership. And that gives you about 32 minutes. Or we hung out for a while and did nothing. And then between 11:17 and 11:55, we were driving back to our warehouse. And that should be 38 minutes. Okay. So our total time is 70 minutes, which when I divide it by 60 to get hours should give me 1.17-ish hours. Good. Okay, so now let's look at our distance. Our distance, we drove 13.2 kilometers, and we drove back the same way, which means that's another 13.2. So if we multiply those by 2 or add them, we're going to get 26.4 kilometers. All right, velocity is equal to rise over run distance divided by time. So we went 26.4 in 1.17, which should give you 22.6 kilometers per hour. And what does this information tell us? Well, maybe they're both in the suburbs with lots of stop signs and stoplights, or maybe there was traffic, but you certainly weren't cooking it from one highway exit to another to get from this warehouse to the dealership and back. Velocity, acceleration, time graphs. Okay, so we're going to start by filling in the thing. And on this thing, it was actually miles per hour, so I kind of made it disappear. But we have points every 2 seconds, and we're going to say that this is a velocity on the y-axis, and it is going to be in kilometers per hour. So just looking at the graph, okay, looking at the time, it looks like, well, nothing's happening there. And at 2 seconds, it looks like that we have a velocity of 28 kilometers per hour. And at 4 seconds, it looks like we have a velocity of 45 kilometers per hour. At 6 seconds, it looks like we have a velocity of 58 kilometers per hour. At 8 seconds, let's say it's 68. And at 10 seconds, let's say it's 52. Okay. Now, when we do acceleration calculations, we always keep our acceleration in meters per second squared. So velocity in kilometers per hour is not useful to me, but velocity in meters per second is. And the conversion, as we said before, times 1,000 divided by 3,600 to change both those units. But if you want to shortcut it, like I know some of you guys are doing already, you're just going to divide by 3.6. So to get from here to here, which will be the same speeds, just in different units, I'm going to divide each number by 3.6. 0 stays 0. This becomes 7.8. This becomes 12.5. This becomes 16.1. This becomes 18.9. And here we're at 14.4. Okay, so now let's start talking about the other stuff that we've got some numbers in there. Once again, slope remains rise over run. Okay. And when you do that, you get acceleration. So on a distance time graph, like before, our slope represents our velocity, but on our velocity time graph, our slope represents the acceleration. Okay, so if you want an average acceleration between 2 points, and we're going to make a hideous triangle again. So, not really sure why it's doing that. Come on. And then, honestly, I'm just going along the bottom with my other piece. I'm not even trying to draw that line. So I'm going to make this thing here. And if I think about, oh, no, that should be straight. Anyway, so this beautiful line, which in theory would be straight, would represent my average acceleration between 0 and 8 seconds, because I'm going from 0 to 8 seconds to get to this point. So I see that my change in x, or my run, is 8. And I see that my rise is 68, but I'm going to write down 18.9. okay? Because that is a useful thing to me. So if we're thinking about the average acceleration between this time, we're going to take 18.9, okay, our change in velocity, and we're going to divide it by 8. And we get an average acceleration of 2.36 meters per second squared, our unit for acceleration. And that's fine. That's a positive acceleration. We're getting faster. We can see that because between 0 and 8, our velocity has gone from 0 to 68 kilometers per hour. That's an increase. So what happens when we look at, say, between 8 and 10 seconds, and we have what's going to make a negative slope? Well, first, let's do the math. So at 10 seconds, our velocity is 14.4 meters per second squared. At 8 seconds, our velocity was 18.9 meters per second. 10 minus 8 gives us 2. And then when we do that math, we get negative 4.5 over 2. And that is, sorry, I'm making it really tight, negative 2.25 meters per second squared. Okay, sorry, I'm going to rewrite that. Negative 2.25 meters per second squared. Okay? And when you get that negative in acceleration, that means a deceleration. It means you're slowing down. And if we look at our kilometers per hour, yeah, at 8 seconds we were going 68 kilometers an hour. At 10 seconds, we're going 52 kilometers an hour. So logically, we are slowing down. And if you flip your numbers and do 18.9 minus 14.4 and get 2.25 meters per second squared, a positive number, that's fine. That just means you know enough to say like, oh, well, my second speed is slower than my first, so therefore I must be decelerating. And that is good. That is good and right. Okay, so our maximum acceleration, once again, is going to be when we have a slope that is the steepest, okay, when we cover the most, or we have the biggest change in velocity for the shortest amount of time. And then usually, right when we're starting away, I have no idea where my thing just went. Whoa! And then more of a minimum one would be a flatter slope, so less change in velocity. When do we see constant velocity? Or what happens when we have constant velocity? Well, if you think about it, acceleration is a change in velocity. So if I'm driving along at 50 kilometers an hour for 3 hours, my change in velocity is 50 minus 50. My change in time is 3 hours. I get 0 over 3 equals 0. So when you have constant velocity, just know that your acceleration is 0. So let's look at a couple problems. Okay, so here's our calculations, and here's the same thing. Our slope is equal to our rise over run, and these are the different versions of it. Okay, here we go. It takes 1.5 minutes. There's a time. Okay, for a truck climbing a hill to go from 85 kilometers an hour to 70 kilometers an hour. What is the average acceleration? So I wrote down my time already. This time, I'm not going to change it into hours because when we do acceleration, we're in meters per second squared. So I'm going to take my 1.5 minutes and I'm going to multiply it by 60. And that is going to give me 90 seconds. Okay. I have an initial velocity and I have a final velocity, v1 and v2, vi, vf, whatever you want to call them. Originally, I'm going 85 kilometers per hour. And if I divide that by 3.6, I'm going to get 23.6 meters per second. And 70 kilometers an hour, and I'm going to do the same thing, divide it by 3.6, and that is going to give me 19.4 meters per second. These two values give me my change in velocity. So if I want my acceleration, I need to know my change of velocity. 19.4 minus 23.6. Do that math first, and you're going to divide it by 90. When you do that, you should get like negative 4.2 divided by 90, and that equals negative 0.046-ish meters per second squared. So I'm slowing down. Of course I'm slowing down. I'm going up a hill with a big truck. Okay. but I'm slowing down really slowly because you don't slam on your brakes when you go up a hill. You just kind of chug away, and if you're driving the Kia Sorento, it just kind of dies on you, and you can't do anything about it, but that's how it goes. So you're going to see a slow deceleration, and that makes sense. So let's do a more complicated one. So we have a highway speed. Oh, no. Oh, I don't know what's going on here. Okay. And that's what we want to get to, 100 kilometers an hour. Okay, and we have an acceleration. And we want to get an initial speed, so we're looking for v1. Well, let's do some math. If we're looking for a velocity, we have velocity equals acceleration times time. And I've got a 3, and I've got a 4, and I've got 12 meters per second. Now, when you're using this formula, the velocity you're solving for is the change. So I'm going to take the 12, and I'm going to multiply it by 3.6 to get me back up to kilometers per hour. Okay, and that should be 43.2 kilometers per hour. And remember, that represents a change. So if I started at v1 and I added, let's do the long way, an acceleration, and I changed my velocity by that much kilometers per hour, and then I got to 100 kilometers per hour. So what was my initial speed? 100 minus 43.2, which is 56.8 kilometers per hour. So you hit that on-ramp at 56.8 kilometers an hour, you accelerated pretty aggressively for 4 seconds, and you ended up hitting 100 kilometers per hour. Next, we're going to just briefly touch on Ohm's law, and you know that's our triangle that has, come on baby, V or E, whatever you prefer, is equal to current times resistance. So same. Look at the question. We're given a resistance. It's 35 ohms. We are given a voltage. It's 10.5. Whoops, 10.5 volts. Okay. What's our math? If we look at our triangle, if we want to solve for the current, we're going to take the voltage, the 10.5, and we're going to divide by the resistance. When we do that, we should get 0.3 amps, so a small current. So will it blow a 2 amp fuse? No. It should be fine. Okay, let's look at our second one. This time we have a resistance. We have a current, 300 milliamps, but I'm going to divide it by 1,000 to change it to amps. Keep the base unit when you do this, so 0.3 amps. Okay, and we're solving for a voltage. So looking at our triangle or formula sheets, we know that the voltage is going to be the resistance times the current, which is going to give you 600 volts. Done and done. These questions are pretty straightforward, so I'm expecting you to do well on them. Let's look at series circuits. What do we know about series circuits? We know that the sum of the resistances, RT, is equal to R1 plus R2 plus R3, however many resistors. Here we have 3. So in order to find the total resistance for this circuit, let me just fill in my thing here first. I've got 7, 9 ohms, 21 ohms. Okay. All right, so to find this value, 7 plus 9 plus 21 should give you 37 ohms. And like I said, when you have 2 pieces of information in a column, you have the math to get the the total current is equal to the total voltage divided by the total resistance. So we're going to take 54 and divide it by 37, and that should give you about 1.46 amps. You can round to 1.5, but just make your your answer is a little different. Now, what do you know about current in series? And this is important. You have to remember this. Current in series is the same across all resistors. So we're going to have 1.46 amps everywhere. That's fine. How do I solve for each voltage? 7 times 1.46, 10.22 volts. 9 times 1.46, 13.14 volts. 21 times 1.46, 30.66 volts. Now, ideally, if you add those things together, 30.66 plus 13.14 plus 10.22, you should get your source voltage. In this case, I think they're going to be like 54.02 volts. Close enough. That's because of rounding. All right, parallel circuits. So I'm going to fill in my resistances that are given to me. 7 ohms, 9 ohms, and 12 ohms. So what do we know about parallel circuits? Well, finding the total resistance is a pain in the butt, but that's just life. So when we look at a parallel circuit, we are going to have to find the resistance by using the reciprocals. So the total resistance, the reciprocal of the total resistance, will be equal to 1 over 7 plus 1 over 9 plus 1 over 12, our three resistances. Okay, and that's where those numbers are coming from. Now, I talked in class about using the reciprocal button on your calculator. That's super handy. At the end of the day, do what you got to do to get these three fractions added together. You can use decimals, but you should get this when you do those three fraction additions. Now, make sure you know to get the reciprocal, you are going to take that answer and do this math, or press the reciprocal button on your calculator, and you're going to get a total resistance of 13.1 ohms. And that should be good. Oh, no, this is the wrong question. Never mind. Let's erase that. 1 second. We'll try the eraser. See if this works for me. My bad. I was wondering why it was higher than everything else. And let's go back to the pen, hopefully. There we go. Okay, so let's look over here. 2.96 ohms. Better, better, better. It should be smaller than the branches. Okay, 2.96 ohms. All right. Once again, you've got voltage. You've got resistance, which means you have current. Just make my decimal a little better. Oh dear. So you have current, which is going to be equal to 4.05 amps. 12 divided by 2.96. Okay. So is current the same in all three branches? No. Current splits when you go into parallel. It doesn't split evenly unless all the resistance are the same value. It likes the path of least resistance. So I expect to see the most current across R1 and the least current across R3. But what I do know about parallel circuits is the voltage is constant across all the loads. So here, because I don't have anything other than this one parallel branch, I know that I'm going to drop 12 volts here, I'm going to drop 12 volts here, and I'm going to drop 12 volts here. And then I just have to do the math. 12 divided by 7, 1.71 amps. 12 divided by 9, 1.33 amps. And 12 divided by 12, 1 amp. And once again, when you add 1 to 1.33 to 1.71, you should get pretty close to your total circuit current. Okay? All right, so let's ramp it up. Combined circuits. So combined circuits are all about redrawing. I've got a 10 ohm here, I've got a 32 ohm here, and I've got a 19 ohm here. Okay, so when I look at this circuit, I kind of start and I go through, and I just have one parallel branch. This one's pretty easy, right? So I have one parallel branch, but I have two resistors in the top part. So they're in series with each other, so I can add them. And I can really, what I'm doing is I'm creating an equivalent circuit, which, pardon my drawing, is going to look like this, where this is the total of R1 plus R2. 10 plus 32 is 42 ohms. This remains 19 ohms. So now I'm just solving a parallel one. And the bonus is I'm solving a parallel circuit which has only two branches. So I can use that cheat where I can find the total resistance of the parallel thing is equal to the product of the two resistances divided by the sum of the two resistances. There we go. And you're going to make sure that you do that addition. So you're going to take whatever it is and divide it by 61. All right. When you do that math, this time, I should get my 13.1 ohms. Perfect. Okay. Here we go again. 115 divided by 13.1, 8.8 amps. So I know that it's not going to be 8.8 amps in both branches. I know that it's not going to be 4.4 amps in both branches because they're not equivalent, like 42 and 19 aren't the same resistance. So I just need to look back at my original picture, and I'm looking for something because the only place I'm dropping the voltage is across this parallel bank. So I'm looking for a single resistor where I can drop all 115 volts, and that's at R3 here. So I know that R3, all the voltage drops. And then once I do that, 115 divided by 19 gives me 6.1 amps. Okay, so I know 6.1 amps went down here. How many amps went up here? Well, that's just subtraction. 8.8 total current. Subtract 6.1 that went into the R3 branch, and that should leave you with 2.7 amps. Now, R1 and R2 are in series, so I know that each one of them gets 2.7 amps. And then the math, just multiply. 2.7 times 10 gives me 27 volts here, and 2.7 times 33, I can't even read my own writing, but I think it's 86.4 or 88.4, something like that. And once again, you're looking for that to total approximately 115 volts. So let's keep going with these and do a few more examples. Okay, got a lot going on in this one. But the first thing you're always going to do is make it look like something more friendly. And we're going to do this in a couple steps. First, we're going to kind of do the same thing we did in the last one. And there's my R5 just floating. Whoops, floating over there. There we go. Boop, boop. I've got an open in my circuit apparently. Okay, put in my values. R1 is 5, R2 is 10, R3 is 4, R4 is 20, and R5 is 8, and 115 is a voltage. Okay, so my first simplification is to combine R2 and R3. They're in series with each other, so I can just add them. This is equivalent to 14 ohms. My next simplification is going to be to make 3 resistors in series. And all I'm doing is taking this 14 and 20 piece and changing it into something here. Okay, so I'm going to use the cheater. R equals 14 times 20 divided by 14 plus 20. Okay, oops, it's very ugly. So we're going to get, hold on, I've got to get another piece of paper here. I'm looking at the wrong page again. Okay, R is equal to 14 times 20 times 14 plus 20, and you should get about 8.2. Oops. Okay, so now my new circuit, I go through that R1 in series. I've made an equivalent resistance for all this hot mess, which is 8.2, and then I go through my R5, which is 8. And at this point, I can add them. 8 plus 8.2 plus 5, total resistance, 21.2. Step 2, same as always. 115 divided by 21.2, 5.4 for the circuit current. Okay, now I look at my picture. Who gets 5.4? Anyone who's in the outermost circuit in series gets 5.4. So I look and I see R1 is a plain old series resistance. It gets that. And I see that R5 is plain old, so it also gets that. Then I do some math. 5 times 5.4 gives me 27 volts here. 8 times 5.4 gives me 43.2 volts. Okay, so now I want to know about the voltage drop in the parallel branches. So I know that I had 115 volts and I dropped 27 and I dropped 43.2 and I have a leftover that is 44.8 volts. Okay, so when I look at this picture, I'm going to send 44.8 across here, and I'm going to send 44.8 across the 20 ohm. The problem is this 14 is equivalent. It's a 10 and a 4. So some of it's going to drop at the 10, some of it's going to drop at the 4. So I'm going to ignore that branch for now, but there's only one resistor in the bottom. So I know that R4 is going to drop all 44.8. Okay. And if I want to find the current across R4, 44.8 divided by 20 gives me 2.2-ish. Excellent. So now I know that I had 5.4 amps coming up to that parallel branch, and that 2.2 amps went to the bottom part. So to find the part that went to the R2 and R3, 5.4 minus 2.2 equals 3.2 amps. R2 and R3 in our original drawing are in series, so they're each going to see that 3.2. And then you're going to do the math to solve the rest of the circuit. 10 times 3.2 is 32 volts. And 4 times 3.2 is 12.8 volts. Okay. And like I said, my questions could be anything. They could be like, what's the current across R3 or the voltage drop at R5? But when you do this table, you know everything. So you're ready for any question I'm going to throw at you. Let's do one more example. Ramping it up even more. I don't think we've done one like this. So we have a lot going on in this picture. First, I'm going to fill out my table. R1 is 5. R2 is 20, R3 is 5, R4 is 6, and R5 is 10. So pure series components, I only have R5. I've got a lot. I've got like a double down parallel thing going here, but that's fine because I can flatten this into an equivalence resistance, change R2 and R3 into one thing, and then I can add that to the 4, and then I can flatten again, and then I will have a relatively simple circuit. So let's draw what we're going to do. So we're going to come in, there's our R1, and we're going to change R2, R3 into something. And we're going to leave R4 alone, because it's still in a series parallel there. And then we have R5 just floating around out here. For this one, oops, not that one. For this one, the R2, 3 is going to be 20 times 5 divided by 20 plus 5, which is going to be 100 divided by 4. Sorry, 100 divided by 25, which equals 4. So we get, this is 4 amps right here. So now I have 4 here, I have 6 here, I still have 5 here. It's not super exciting to me right now, and I have 10 down here. So next step, you got 2 in series, simplify it. So simplify, simplify. Leave the 5. This is going to be added together, and you have your little 10 floating down here still. Okay, 5, 10, 10. Here, same trick. The resistance of that is equal to 5 times 10 divided by 5 plus 10. So your resistance is going to be 3.3 ohms. Excellent. And now we essentially have a circuit that looks like this, where you have 3.3, whoops, and you have 10, and this is series, so you add them together. I know you did all the work up here, but don't forget about the 10. 3 plus 3 plus 10, 13.3. Okay, 80 divided by 13.3. 6 amps. Right back to the original picture. Who gets 6 amps? The only place that current hasn't split is right here, because it split a whole bunch in here and it came back to 6 amps. But R5 gets that full 6. So we're going to write 6 here. And that means that we're going to drop 6 times 10, 60 volts across R5. Wow, we used up a lot of it. So what do we have left over? $20 volts for the rest of it. Okay. Which one of these things is actually going to get 20 volts? Well, if I look here, there's a whole bunch going on, like another parallel thing and another resistor. They're all going to get some amount, but the top branch only has one resistor. So I know that if I look at R1, it's going to get the full 20. 20 divided by 5, which means 4 amps went up there. So I used 4 amps this way. What goes this way? 2 amps. Why? Because 6 minus 4 is 2. Okay. Now, it's going to split again in the 2, 3, so I'm going to ignore that one for the moment, and I'm going to look over at the 4, because it'll come back together and be 2 amps across the 4. So I can go over here, put my 2 amps in, 6 times 2, 12 volts. Okay, so that means I had 20 volts in that entire branch. I had 20 volts coming in here, right? And the 20 volts we had there. I am going to use 12 of it here. So the leftover for this little R2, 3 parallel bank is 20 minus 12, 8 volts. And R2 will get 8 volts, and R3 will get 8 volts. And then 8 divided by 20, 0.4 amps, and 8 divided by 5, 1.6 amps, and guess what? 0.4 plus 1.6 equals 2. So that's perfect. All right. Let's talk the last topic for this little lecture. What happens when you have opens in series? What does an open in series look like? It looks like you broke a wire. So let's say we should have had 2 resistors, and instead we just have, what happened here? 1. There's no connection, so there is no current flowing. And the resistance, we call it infinite, right? Because it's just not going to happen. So it's infinitely resistant. So that's my infinity symbol. What about in parallel? Pure parallel? So the resistor that was there is gone, right? So what has it turned it into? It's turned it into a series circuit. Now the series circuit is always going to have more resistance than the parallel circuit. So your resistance is going to go up. And if we know that V is equal to IR, and the R goes up, but the V isn't changing, I have the same supply voltage, the current must go down. Okay, there we go. Now, let's say we have a combined circuit. There we go. La, 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 la. So we kind of have to have 2 situations here, the series and the parallel. If I open across the series part of the circuit, what happens? It's the same as the other thing. We have no current flowing. I don't know why I keep doing that. I have no current flowing. Make a 0. There we go. No current flowing. And then the resistance is infinite because there's no current flow. Now, if I open it up in parallel, you're just going to get rid of, say, this branch, and it becomes a series circuit. And like we said, when you have this series component, your resistance is up, and you're going to see a drop in current. Shorts. So if you have something in series, and you create a short. A short is like when you take a resistor and you make it a wire. So it really kind of turns this little circuit into a 1 resistor circuit. Resistance is down, therefore current is up. If you are in parallel, and this is a pretty nasty situation if this happens and you don't have circuit protection, because when I take this and make it into a wire, I'm essentially creating this situation, because no current is going to go down the path with the resistance still in it when it can go down a straight wire. So resistance is zero, essentially zero, so your current goes way, way, way up, and you're going to blow your fuse or melt something. And if you have a combined circuit, when you take series part and the parallel part, when you get rid of the resistance of the series thing and make it a wire, you just turn it into a plain old parallel circuit. So yeah, you're dropping some resistance, right? So you're increasing the current. Likewise, if you make this a wire, you're going to drop the resistance and increase the current. So just be aware of how to walk around those kind of situations. So that's it for all now. Hopefully this works. I have no idea. I have no interest in rewatching it, so I'm hoping it's good.